Hello everyone. In this video, we will be discussing about static load and its determination. So, what do you mean by static load? We know that all the machine members are subjected to different types of loads that may be acting because of energy, torque or power transmission, their self-weight, frictional resistance, inertia or centrifugal forces are due to temperature gradient. So load may be classified as static or dynamic. So a static load is a load which does not change in magnitude or direction but gradually increases to a steady value. Example, dead weight of machine element. Then what is dynamic load? It is a load which changes in magnitude or direction or both with respect to time. Example, load acting on the connecting rod of an internal combustion engine. Then impact load, so which is nothing but the load applied with certain velocity. And next is shock load, where the sudden application of load on the machine component, we are calling it as shock load. So all these are the types of the dynamic load. So now we will discuss in detail about all the stresses. First we'll start with the axial stress. So when I speak about the axial stress, we have two different types of stresses. First one is nothing but direct tensile stress and second one is the direct compressive stress. So tensile stress can be defined as when the fibers of the component tend to elongate under the external load, stress developed in the component is called the tensile stress. On the other hand, when the fibers tend to shorten under the external load, stress developed in the component is called compressive stress. So, theoretically, how tensile stress can be written as means, here you can able to see sigma T indicates tensile stress which is equal to load by area, that is P by A. And for the compressive stress, which is denoted as sigma C, which is again equal to P by A, that is load by area. Here P is the external load and A is the cross sectional area of the component. And here you can able to see for both the tensile stress and compressive stress, both the theoretical formula, it should be less than or equal to the normal stress. So here the sigma and sigma C is nothing but the allowable stress. This is nothing but the allowable stress, the permissible stress, or the design stress, which means with by considering the factor of safety, this allowable stress usually should be formed. And sigma C is nothing but either tensile stress or compressive stress. So from the formula P by A equal to sigma or P by A equal to sigma C, the minimum cross sectional area required to withstand a known load, where P can be determined for the following allowable stresses. Next is shear stresses. So how can we define shear stresses? Means when the external load acting on the component tends to slide the adjacent planes with respect to each other, then the resulting stresses on these planes are called direct shear stresses. So, and even it can be also defined as a change in right angle of a shear element. So on the surface, if you are applying some load and due to that load, if any stresses is produced on the component, means then we are calling that as the shear stress. Next is a bending stress. So when a machine member is subjected to a bending movement, so the tensile stress develops on one side on the neutral axis and the compressive stress on the another side. Therefore, the outside fibers are in tension and the internal fibers are in compression. So the bending stress at any fiber is given by sigma B indicates bending stress, which is equal to m into y divided by I, again which is less than or equal to the allowable stress. Here m is nothing but the applied bending moment, I is nothing but moment of inertia of cross section about the neutral axis, and y is the distance of the fiber from the neutral axis. Here the moment of inertia value will vary, depends on the cross section. Then the distribution of bending stress is always linear and the stress is proportional to the distance of fiber from the neutral axis, and it is maximum in the farthest fiber. Next is torsional shear stress. So the stress which is induced in the machine member, if it able to resist the action of twist, then it is called as the torsional shear stress. The formula is nothing but the torsional shear stress usually denoted with a tau symbol, which is equal to T into R divided by capital J. So where T is nothing but applied torque and small r is nothing but the radial distance of the fiber from the axis of rotation, and the capital J is nothing but polar moment of inertia of the shaft about the axis of rotation. So next one is the bearing or the crushing stress. So crushing means to press or squeeze with a force that destroys or deforms and it squeezes into the small fragments. So crushing or bearing stress is defined as compressive stress developed at the surface of contact between two interacting members that are relatively at rest. And the crushing stress is assumed to act uniformly on the projected area. So the crushing stress can be written theoretically by load by projected area. So load can be denoted with capital P and projected area can be denoted with D into T again, which is less than or equal to the allowable crushing stress. And if small n is the total number of rivets used, then the total projected area will also become NDT. Now next is combined loading and principal stresses. When the machine component is subjected to only axial load means like either tensile load or compressive loads, then bending moment or torque, then the type of stress whatever is produced we call it as a uniaxial state of stress, which we discussed just now. But in reality the machine components are mostly subjected to combination of loads. That is, example, if you take a transmission of a shaft where that particular application is subjected to bending and torsion at the same time. So these kind of combined loads we are calling it as a combining loads lead to the complex state of stress. So for these kind of applications, the state of stress at a point is the totality of all the stress vectors acting on it. It means we need to find out what is the bending stress acting on it, what is the torsion stress acting on it, and the same thing if any tensile or axial stress is also acting, that also individually we need to find out. So for design purpose it is very important to know that the state of the stress whatever we are determining are in the critical planes, the respective critical stresses, and we need to relate them into the strength of materials. Here you can able to see some of the real life examples of the combined loading. So you can able to see I have taken a crankshaft example where a torsion will be there, where a bending will be there, and even an axial also will be there. And apart from that, here one more important concept also is hidden, that is nothing but fatigue. So that also will be discussing in the upcoming videos. And second example you can able to see the connecting rod, and next one is nothing but a coupling, you can able to see so how it works, and a thrust and torsional shear, a lifting jack, a screw jack, you can able to see that. So here also torsion will be there and some bending will be there and some axial load also will be there. So here a propeller shaft if you take means where the combination of axial load, bending and torsion all three will be there. Example we can take as a propeller shaft. So from our discussion we come to know that we can classify loads into three major categories, that is uniaxial load, biaxial load and biaxial with the shear load. Here I have shown the pictorial view of uniaxial loads, biaxial loads and biaxial with shear loads. So what is the formula we need to remember means uniaxial means always x direction only we will be considering, and the formula is that is maximum shear is always equal to half of the normal allowable stress. And coming to the biaxial, where the maximum shear which is equal to sigma x minus sigma y divided by 2. And moving to the biaxial with shear, the maximum shear which can be calculated by the formula square root of sigma x minus sigma y by 2 whole square plus tau x by square. And you can able to see the shear how it is acting on and how the uniaxial and biaxial load is acting on it. All these things you can able to see it very clearly here.